Okay, let's talk about some other compression techniques now. So I guess the last thing that we went over was probably the Huffman tree, right? As far as compression goes. Is that the last thing we talked about? We went through that last week. Well, I kind of briefly touched on like the JavaScript, compressing that JavaScript file, right? Where you had some knowledge of the contents of the file, and so they were able to remove some information. It wasn't lossless, a lossless way to compress it, but they were able to compress it and come up with a file that was still usable, but like a fourth the size of the other one because of having knowledge of the JavaScript language. So there are other compression techniques, and some of them are very specific to whatever it is that you're trying to compress. But let's talk about a generic one that's called LZ77. It's called it's 77 because it was first published in 1977. And so this technique looks for repetition in a string of data. Looks for repetition in data, and instead of encoding duplicate data twice, well, I'm just going to say instead of encoding duplicate data, specifies how far to jump back and how many characters to repeat. I want to make sure you kind of understand the basic concept behind how that compression technique works. Give you a moment to think about that definition, write it down, whatever you want to do there. So it gives an example of in the book of the word hello. So we have a document with the word hello in it, right? That might show up multiple times in that document. And if we're talking ASCII, hello is going to take up how many bytes? Not bits, but bytes.
That would be 40.
5, right? Because it's a byte per letter in ASCII. ASCII is 8 bits per character, so 1 byte per character. So this would be 5 bytes or 40 bits in ASCII, right? So what this compression technique would do in a situation like that is if it encountered the word hello the first time, it would just encode it normally the first time, right? Just like it would normally be in ASCII. But then when it encountered it the second time, let's say it encountered it the second time, and how many characters did I say it was? 30 characters after it appeared the first time. All right, 30 characters later in the string as you read the file from beginning to end, right? And so what LZ77 does is it says instead of storing those 5 bytes again, those 40 bits again in the file, what if instead we stored 8 bits the second time that it shows up, store 8 bits and use the first 5 to say how to know how far to go back. Use the last 3 to know how many bits to repeat. So it uses a technique like that, right? 8 bits may not be enough depending on how far you're jumping back and forth, right? But if you think about that, like in this case here, we could tell it with only 5 bits, we could tell it that we need to go back 30 characters. And the reason that we know that is if I say 2 to the 5th power, what's that number? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, right? 2 to the 5th power is 32, so I can this would be enough bits for me to say go back 30 characters. That's why I picked 5 bits, right? And then the 3 bits would be used to tell me how many characters to repeat. I need to be able to say we're repeating 3 characters, and so I can. All I need is I would only need 3 bits. I wouldn't even need 3 bits actually. I can do that with just 2 bits, but 3 bits to tell you to go a little bit to be able to do a number bigger than. Oh no, I'm sorry. We got to repeat 5 characters, right? So I would need 3 bits because 2 to the 3 equals 8, right? 2 squared is 4, so I don't quite have enough bits to say repeat 5 letters, but I could do 2 to the 3, which would be 8. And so with 5 and 3 bits, a total of 8 bits, I could say go back 30 characters and then copy 5 of those characters. Does that make sense to you guys? Sort of thought process. That's a simplified example, right? But that's in essence how LZ77 works, right? It says don't store hello again, which would require me to store another 40 bits, right? But instead, I'm going to store a much smaller number of bits to tell you how far to go back and how many characters to repeat. Okay, so like in this example, we were able to go from another 40 bits in the file to only 8 bits, so significant savings, right? So that's the idea with LZ77. You don't repeat data. You're looking for data that repeats itself, and you don't repeat that. You instead say, basically take a copy of that. The file knows how to take a copy of it. When it's compressed, it knows to take a copy of it. So when you uncompress it, it's a lossless technique. When you uncompress it, you get the original file, right? It looks just like the original file when it's uncompressed. The nice thing about LZ77 is this is not dependent, unlike the way the Huffman tree model works, where you're not looking at actual bits, but you're looking at characters, something that the bits represent. This model here, you can just look at raw bits, right? You can just look at anything that you can find repeating patterns in, and then you can build an algorithm that says use those repeating patterns to compress the file. And so this isn't limited to just text. Repeating binary patterns would work just fine, and so you could use this for image files, video files, right? Any kind of data besides text files, you could compress it. So just kind of give you a sense of any questions, I guess, about the basic process of how L77 works? Or LZ77, sorry. LZ77?
So it's basically, it's going back and it's finding that data previously, so it's basically, it has basically a link here to go back to here.
Yeah, right,
So
exactly.
I can find that,
Right.
put it here.
So that's how it compresses it down. And so when you uncompress it to see the original file, it just rebuilds it based on those instructions, right? Make sense?
Yeah.
Would you have to have metadata for?
You'd have to have most of these techniques. There's some sort of metadata that tells you kind of what maybe, for example, maybe it analyzes the file the first time it goes through, and it figures out how many bits it's going to need to store that back and forth information, right? So there may be metadata that tells you that's the number of bits that we're looking for to store the jumping back and forth process, right? So maybe some instructions for that. So yeah, it'd be a little bit more than just the raw savings that we're talking about here, right? Because most of these have to have some sort of map at the beginning of the file to tell you how to uncompress it. So let's just to get a sense in size difference and how this might help with, say for example, an image. He tells us in the book that in ASCII, for our particular book, 20,000 characters would be about 15 pages in our book, right? For a book this size, about 15 pages would take up 20,000 characters. And so with ASCII, if each character is represented by 8 bits, then that would be about 20,000 bytes. So 20,000 bytes, or to convert that to kilobytes, it would be about 19.5 kilobytes. All right, that's just for text. So he's just trying to give you a sense of how much smaller text is than like graphics or video, right? Let's think about an image. So for an image, Remember we talked about RGB, which stands for what?
Red, blue.
Red, red, green, blue, right? Red, green, blue, and do you guys remember how many bits we used for each red, green, and blue?
250.
Is that 256?
It's 256, which is 8 bits, right? So 1 byte, all right? When you were thinking 2, you were thinking about maybe the black and white? Is that what you were thinking about? So it's 8 bits apiece. So 8 bits for this, 8 bits for this, right? 8 bits for this. For a total, so for 1 pixel in RGB, it's a total of 24 bits. That's kind of weird for, there we go, 24 bits, right? For 1 pixel. All right, so let's think about that. Let's think about a tiny image. With our screen resolutions today, if we had a 400 by 400 pixel image, right? So 400 by 400, how many total pixels is that in that image? Well, it's 400 times 400, right? So it's like 160,000, yeah. 160,000 total pixels, right? Just doing the math here. 160,000 total pixels, and each pixel requires 24 bits, all right? So that means, if we do the math with that, if we have 160,000 pixels times 24 bits, that's going to give us the total number of bits, but we're trying to figure it out in bytes. So now we're going to divide that, divided by 8 bits per byte, and then we're going to divide that by 1024, or on the bottom here we got 1024 bytes per kilobyte. I'm just kind of doing the math here. So when we punch all that in our calculator, we come up with this, 468.75 kilobytes. All right, that's for a tiny image, 400 pixel image. Look at how much larger that is than 15 pages of text in our book, right? So just a small image using the RGB color model is huge compared to text, right? And so this LZZ compression techniques like that are critical for being able to work with images. It would be a lossless way. LZ77 is lossless. LZ77 would be a lossless. And by the way, that was the answer on the quiz, right? Lossless would be a lossless way to compress an image. So there are other techniques like JPEG compression, which we had a homework assignment for. And what did we find out with JPEG compression? If we took it down low enough, what ends up happening to the image?
Pixelization.
Pixelization, right? So that would be not a lossless technique, but the compression they're using there would be a lossy technique where you throw away the less important data. But LZ77 would be a lossless option. Not gonna get as small a number as you'd get for the lossy one, but you're gonna suffer in quality if you do the lossy one. All right, any questions about LZ77 and how that technique works? They're clapping. They appreciated it over there. Thank you. Thank you. My class is not as excited about it as you are. Thank you, Mason. Thank you. Thank you. All right, so let's talk about digitizing images. And I tried my best to use a different example than the one that he had in the book. Digitizing images. So just to get you thinking about, now that we're starting to think about some of this stuff, because I know, you're taking a class, it's computer science principles, and if you're like me, you're going, I just want to start programming. When are we going to start writing some code, right? But you're starting to, like even building a Huffman tree, we're starting to get you to think about how you need to consider things before you start writing your code, right? As you kind of work through these problems in your mind and lay things out and try to do things most efficiently. And so one of the things that I want you to think about is how do I take a series of zeros and ones And how does that get converted to an image on a TV monitor, right, or on a computer screen? How does that work? How does that process work? So we want to kind of talk through that. And he used this example in the book, and I was trying my best to think of a different example, because this is not, he says this is an image, but it's an image of a word. So I was like, maybe I could do an actual image, and we could do one in class. But in order to teach the compression portion of it, his word actually worked really well. And I'm glad I walked through it, because he made several mistakes in the book on doing this, all right? So let me open my book up so I can tell you where those mistakes are so we can count them. I was going through this going, man, I totally need to write this guy an email and say, this needs to be fixed right here, because this is going to be confusing to somebody that doesn't know. There's one thing, the word on page 78 in your book, if you have your book, this was a minor issue and something that spell check wouldn't catch, but in the middle paragraph there on page 78, it's talking about LZ77 compression. Right after the statement that's got parentheses around it, it says, showed up earlier in the text, the algorithm would specify how for to jump back, and it should be how far to jump back. All right, so if you see that word and you want to correct that in your textbook, it's in the middle of page 76 there. How far to jump back is what it should say in the code there. All right, so the image that I'm about to draw on the board, you can see it at the top of page 78. And the image is the word high, and it is 1, 2, 3, 4, 5, 6. So it's going to be, so I'm going to try to draw this 1, 2, 3, 4, 6. We're going to go down here, and then we're going to go 5 down. 1, 2, 3, 4, 5. So I'm drawing this grid here to try and represent your computer monitor, right? These are the pixels on the grid, right? And so this particular digital image, we're going to block this in, and we're going to block this in, and this, right here, right here, right here. And so we've got a black and white image, or in my case, a blue and white image. And so these are all the squares that are going to be black. And then all the ones I didn't color in are all the white squares. And so it's a digital image of the word high. Okay? And so how would you go about digitizing this image? So that's what we're going to kind of walk through. So this image is how many pixels wide? If you count the number of blocks across the top, it's 6 pixels wide. Right? Is that not right?
Yeah.
Okay, yeah. And then how many pixels, what's the height? 5, right? So it's a 6 by 5 image. Whenever you see your images, like if you check the properties on your computer and you look at the size of the image, it always lists the width and then the height, okay? So this is a 6 by 5 pixel image. And only using black and white. And so what he says in the book is if black equals 0 and white equals 1, and that was the first place he messes up, because he says let black equal 0 and white equal 1, and then when he builds the string down below, he switches those around and he makes white 1 and he makes black 0. So we're going to go through it the correct way. And then you store, so black equals 0, and white equals 1, and you store the image size as 8 bits apiece in the metadata. then we could represent this digital image here with a binary string that looks like this. All right, 0. So we got 5 zeros here. And just for time's sake, I'm not going to put the slashes through there so we'll know the zeros. We can hopefully, since this is a binary string, we'll recognize that these are all zeros. 0, 0, 0, 0, 1, 0, 0. So this right here is the width. And this is the height. And we know that because if we remember, when we're counting in binary, if we have 0, 0, 0, if we just look at 3 bits here, then this represents 0, 1, 2, 3, 4, 5. So this would be 0, 0, 0. This would be 0, 0, 0. I'm sorry, 0, 0, 1. This would be 0, 1, 0. This would be 0, 1, 1. This would be 1, 0, 0. And this would be 1, 0, 1. So that's exactly.
Wouldn't there be another 1 at the end of the height?
Oh, wait a
Because it's
minute.
5?
Wait a minute, I messed that up, didn't I?
There should be another 1 at the end of the height, I'm pretty sure.
1, 1. What did I do wrong here? 0, 1, 1. Oh, this is 6. Sorry. This would be 1, 1. Yeah, you're right. This height would be 1, 0, 1. Right. All right. And I got messed up there because he did that correctly in the book. But if you look at it in the book on page, what page is that on?
78.
He only put 7 bits in the height. You guys see that? So he's missing a 0. There should be another 0 in the height there. So let me change mine here. So we got a 1 there. All right, so now let's talk about pixel data. So if black is represented by a 0 and white is represented by a 1, just kind of going through this, and we're going to do it in chunks of 8, so we'll do it a single byte. So we got a black, white, black, white, black, white, black, white, right? So that's the first 8. You guys see how I'm doing that? Black, white, black, white, black, white, black, white. We're just going through it 1 pixel at a time, right? The computer would know where to repeat because it knows what the width and height is. So it knows when it reaches 6 pixels that we're going to draw the next pixel on the next line, right? So now we're starting from right here. So we go black, white, black, white, black, 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 white. So that black, white, black, white, black, 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 white. That got us all the way there. You guys tracking with me so far? So then it's just black, white, black, white, black, white, black, white, black, white, black, white. It's just black, white, over and over and over again. Black, white, black, white, black, white, black, white, black, white, black, white, black, white. And it turns out that once you get to 6 bits here, that we're at the end of our image. So he just padded this last one with 2 zeros. All right, so if you look at it in the book, he does it in the opposite order. You see that? He does 1, 0, 1, 0. So it's like, okay, we're gonna have to change that up. But is everybody tracking with me on that piece? That makes sense? You see how a computer could totally read that metadata at the beginning so that it knows how far to go across for the width and the height, and then start reading this data here and know what color pixel to put on the screen so that you can represent this image. Does that make sense to you? Yeah?
Yeah.
Okay, good. That's good. I didn't want you to be confused because I'm not sure I can explain that any better. All right. So how many total bits or total bytes are we talking about right now in this image? 6 bytes, right? What were you saying?
No, I was counting the individual bits.
Oh yeah. So bytes, right? So 6 bytes, or since there's 8 bits a byte, or 48 bits, right? So that's how many bits we're using to represent this image right now. So let's talk about how you might use something like LZ77, the LZ77 method, to shrink this down, and what the savings might be. So what LZ77 does is it looks for repeating patterns, right, and tries to build tells you what those repeating patterns are and how many of the repeating items there are. And so what we see with this one here is that if you take this, if you look at this image as groups of 2 pixels at a time, that we've got this repeating pattern over and over and over again, right? Black, white, black, white, black, white. Almost everywhere we have black, white, black, white, black, white, except for this one sequence here where you've got black, black, right? When we hit this part of the H right here. But everything else is all repeating. So if you think about it like this, where the image is really a series of black, white, we're just going to abbreviate that by BW, right? So for BW, we have 1, 2, 3, 4, 5, 6 BWs to start with. Then we have 1 black, black, 1 BB, and then we have 1, 2, 3, 4, 5, 6, 7, 8 black, whites. Do you guys see how that works? How that's repeating that way? Again, he messed this up in the book. Even though he drew it this way, he said in the book that we had 9 black whites and that we had 11 black whites. So I think he must have, when he originally did this, he must have put like another layer on the top here. But if you put another layer on the top and another layer on the bottom, you change the size. It's not a 6x5 image, right? So he must have done it initially as a 6x7 image and then changed it when he was doing the book or something. So it's a little confusing if you go through his scenario there. So what we're going to do, let's say we use, for each run of pixels, we could say something like this. We could say we're going to represent this then with this sequence, what the repeating sequences are using 6 bits. So 6 bits and 4 bits for the length of the run, and 2 bits to represent the pattern. Right, so I could redo this where I can use 4 bits. The biggest number I have here is 8, and so if I go 7 and 8, see this becomes 1, 1, 1, and as soon as I get to 8, I got to use a 4th bit. So if I use 4 bits, I can go as high as the number 8, right? And that's the most repeating ones that we have. So 4 bits would be enough to let me specify the length of the run, and then I could use 2 bits to represent the pattern, right? Because black, white would simply be 0, 1, and black, black would be 0, 0. And so then I could just string all these together, right? And I would have something that looks like, so 6 BW would be, here's the number 6, 1, 0, 1, 1, 0, right? And BW would be represented by 0, 1. And then 1 would be 0, 0, 0, 1, 0, 0 would be the BB. And then for 8, I've got 1, 0, 0, 0, and then the BW is 0, 1. So those 6 bits there could represent all of the repeating patterns in that image. Did you guys follow that? Anybody need me to walk through that again? Because I felt like I was kind of standing in front of the board, and it might be a good idea for me to step back from it. And I'm going to make kind of a break here so that we see this is 0, 1, 0, 0, 0, 1. And I'm going to go ahead and pad these with zeros since we're using 4 bits to represent each of these numbers. And so all I did here is I said I recognize that we have a pattern of 6 black whites. So the binary representation for 6 is 0, 1, 1, 0. And since we said black is represented by a 0 and white is represented by a 1, then we do the binary number for 6, and then we do 0, 1 because it's black, white. Then we have 1, black, black. So binary number for 1, using 4 bits is 0, 0, 0, 1. Black, black is represented by 0, 0. And then finally, the binary number 8 is 1, 0, 0, 0. And black and white is represented by 0, 1. Okay? So we'd still have to have the metadata at the beginning that contains the width and the height. But if you think about it, this is only, what, 6 times 3, that's only 18 bits total. 18 bits for all of that, right? Plus 16 bits here to represent the width and the height. So we're at a total of what, 24 bits? 24, is that right? No, 34. 34 bits, so equals 34 bits versus the 48 bits that we started with, right? So it may not seem like a huge savings for this little tiny image, but it's still 30% smaller than the original one was, right? So if you've got a bigger image, you can just imagine how the savings would be multiplied as far as the file size goes. So that's one way that you could, one, understand how you might represent an image digitally, right? How you would represent that digital image on the monitor. And then two, how you might compress that image in a lossless way to where you don't lose any data in the process. Any questions about that?
So a different image besides just like a word, like that is
Yep.
just black and white would the less quality you get would be this smaller size you get, and it basically is trying to find more patterns.
Yeah, it's
whatever
looking, for patterns. Like this 2 pixel repeating pattern just worked out well for this image, right? But the algorithms are sophisticated enough that it can look for more complicated, more complex patterns, you know, and figure out how, okay, here's the most efficient way to organize this image, to break this image down so that we can identify repeating patterns in it. Does that make sense?
Yes.
Yeah. Does someone have a question back there? No? How's your solitaire game going back there?
I'm actually recreating it using a table.
Oh, are you?
In Word.
Yeah.
I inserted an Excel table. And
Oh, cool.
recreated it.
Okay, excellent.
But yeah, I'm winning on some tricks.
Okay, let me know if, well, it's not, is it solitaire where they jump across the screen, or is it another game where the cards just sort of do the cards sort of do? Is it solitaire that does that?
What?
You never beat solitaire on the computer?
Yeah.
Have you played
Yeah.
solitaire on the computer?
Cards jump across. the
Cards.
screen. Cards.
Yeah, the cards, the playing cards on the computer, they'll like jump across the screen when you win. They just sort of they just move all across the screen. You never seen that? It's a wonderful experience. You know, it's one that you kind of want to get up and run around the room, dance a jig or something when it happens. It's so exciting. All right. So that's kind of the idea behind LZ77, where it's looking for repeating patterns, and it specifies, you know, how many to repeat. It's that sort of idea there. So let's talk about other ways that you might compress images. See how we're doing on time. All right, good. So compressing images. We want to talk about compressing images, and then if we have time, compressing video, and then compressing audio. So compressing images. How might we go about, let me make sure I'm not overlooking anything. Oh, yeah, there's one thing that I wanted to point out about the compression technique that we just used there, where you're looking for those repeating patterns or runs or sequences of data, and then you specify the length of that. That's the name of that type of encoding is called run-length encoding. All right. So this is a lossless compression technique where you look for redundancies or patterns as runs in the code. So you're looking for those repeating patterns, and you think of those as runs, just like we did. We had a run of black, white, black, white, black, white, and then or a run of black, black. And so that's called run length code, is you kind of go through the file and look for those runs, those sequences, those repeating sequences in there. So just want to make sure you know that term. All right, so let's talk about compressing images. We mentioned earlier in the chapter that, yes,
What does that say again? Like conservative R, that word?
Red, we're done.
that,
No, middle line, last word.
redundancies,
Okay.
sorry, it's redundancies, 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 all right? All right, if you wouldn't sit on the back row, Christian, you can see that, okay, man? If you were sitting on the back row and my handwriting wasn't so bad, all right, you can see that. So, are you guys familiar with that word, redundancies? If you say something's redundant, it's like, well, you just said that, but in a different way. There's no reason to tell me that piece of information because it was redundant. So redundant means the same thing over and over. All right, so compressing images. We talked earlier in the chapter about there being a branch of psychology that's called psychophysics. You guys remember that? Psychophysics? Remember, because I said, that would be a cool title. I'm a psychophysician, you know? So I want you guys to be that one day so I can say, I know a psychophysician, you know? People will be like, what? He should be locked up. No. And then I can explain what you do for a living, right? So studies have been performed to determine how many different shades of gray that the human eye can detect. All right? And so there was a study released in 2012 that said we can only perceive about 30 distinct shades of gray. So we have all these different shades of gray, but our brain can only process 30 of those and see a distinction between 30 of those. Well, when we're using, if I do a grayscale image on a computer, it's going to use 2 to the 8 colors to represent that. What's 2 to the 8? That's 256. All right, 256 different shades of gray to display my grayscale image. Well, what's the point in using 256 colors to represent a grayscale image if my brain, see, that's why you guys can't read my writing, because that doesn't look like my at all, does it?
It looks
My-
like
my-
M-U-Y.
It look like what?
M-U-Y.
Right. That's because my brain can't process letters, right? My brain can only see 30 shades of gray. Right? So grayscale image uses 2 to the 8 colors, or 256 colors, but my brain can only see 30 shades of gray. And I'm colorblind, so maybe I can even see less. I don't know. Right? Some of us aren't even able to see that many. And so these are the types of things that psychophysics have made us stop and think about as far as like image compression. Right? When we realize that, well, if I can only see 30 shades, why am I taking up the space to represent 256 shades of gray when the mind doesn't even recognize all those shades are there? And so what we end up doing is we throw away the rest of the data. Because if I throw it away, your brain's not even going to recognize that it's gone, right? So throw away 256 minus 30, right? Which is what? 226 bits of data. And the brain never knows. All right, so that's an easy way to compress the file. Just throw away information that we're never going to recognize. But if I throw away information like that, now what do I call that type of compression?
Loss.
It's lossy, right? This is lossy compression. In other words, when I compress it in this fashion, I cannot go back to the original file, right? That original data is lost. There's no way for me to reconstruct the original one. But you can save a lot of space, and this study in psychophysics has opened up, all kinds of ways to do this type of compression because the brain just doesn't recognize that it's going on. Of course, this is grayscale that we're talking about here. When you start talking about color images, if you use 8 bits per R, G, and B, then it's possible to make over 16 million colors. So using 8-bit RGB, we can make over 16 million colors, which is awesome. But again, psychophysics steps in and says, but we can only perceive of 10 million, about 10 million different colors. All right? The human eye can only distinguish about 10 million colors. Now, when you're talking about number of bits, that's huge, right? That's 6 million colors less than what we have the potential of making with the RGB color model. And so there's no point in keeping those extra 6 million colors in there if the human eye is never going to be able to detect them, right? So this is, again, something that that we can use to our advantage when we're doing lossy compression, right? Now, you guys, it may have been hard to tell, depending on the quality of your original image and your screen resolution and all that sort of stuff. It may have been hard to see, but when I gave you that exercise of compressing JPEGs, looking at the different qualities of those JPEGs as you took how good the JPEG looked as you took the quality down and how that affected file size. If you take it down too far, you get an image that looks basically like the one on page 80. And that one on page 80 there is one that's lossy compression has been used, right? It finally reaches a point where the pixelation is so great your brain begins to detect it, right? It throws away too much color information. And so it's especially true when you've got like a gradient, kind of like you'd have with a sunset here, right? Where the color slowly changes from one color to the next, and you got all these colors in between. And so you can see how the gradient here in this particular picture, you get these kind of distinct bands as the various colors are thrown away. Did you guys see anything that strong when you were doing your JPEG compression, where it was that? Yeah. I tried it on some JPEGs last night because I was trying to show you guys a good example of this, and same kind of thing. It's like it didn't matter how low I took my compression down, it didn't look this bad, right? And even trying to convert it to like a GIF file. I used to see this all the time way back when I was building, when I was taking photographs and then converting it to a GIF file to put on a web page, and it might look like that. So I don't know if the compression techniques have just improved so much now that they're doing a better job of fooling you. I'm not sure really what was involved with that, but I didn't think about trying a nice gradient. That would have been a good idea, because that's a lot of times when you see these bands is when you have a gradient. So you've got all these colors in between to make that gradient go smoothly, right? So then when you start throwing out those colors, the bands become a little more obvious. So let's talk about some common file formats and just let you know, just want to distinguish between these common ones as far as which ones are lossy and which ones are lossless. And when you might use one instead of the other. So PNG, does anybody know what PNG stands for?
Portable network graphics.
Did you cheat?
Found it in the book. Is that cheating?
All right, well, he didn't cheat, he was resourceful, right? So we're going to put you on the board for that, Daniel. Nice job. Portable network. See, the name itself, network, signifies that they were designed, PNG was designed with transferring stuff over a network in mind, right? Portable network graphics. And this is really becoming the most common way typically to put graphics on the web. Not photographs. Photographs we traditionally stick with JPEGs, but other graphical images we're using PNG. And that's mainly because it took a while to get those out there, mainly because browsers didn't support them. And so now they're pretty much supported across the board. And so this is the most common photographic image format out there on the web. So it's lossless. It's based on LZ77 and Huffman trees. How about that? So we know the technology behind PNGs. You've used that in here. These have pretty much, I just want to make this note, pretty much replaced GIFs unless doing animation. So the GIFs are typically only, PNGs don't have an animation option and GIFs do, and so that's typically when people jump to GIFs now. But file size, you'll get generally a smaller file size and a better quality image if you use PNG. Well, I say better quality, which kind of doesn't make sense in light of what I'm about to say about GIFs. But let's go to let's go ahead and talk about GIFs real quick. So GIFs. Does anybody know what GIF stands for? It's Daniel.
Graphical.
Yeah, you're on the right track. That's really all I want to point out, so that nobody ever says GIF again, right? It's not graphical. It's graphical interchange format. So you said the most important part, Nathan, so that's worth putting your name on the board. Graphical interchange format. This is also lossless and uses a dictionary algorithm based on LZ78, which is LZ77's successor. Now I said that the image quality is generally better, and that doesn't make sense if both of these are lossless, because if it's a lossless compression technique, then how can one be better than the other if you're not losing any information? And I'll be honest, I haven't played around enough with this with PNGs to see, but I know with GIFs, at least used to, you could take the number of bits down, and so the number of colors that were saved in the image, you could define that specifically. In fact, you could get down to the custom level and say, I want to remove this color, remove this color, remove this color. And in fact, in Photoshop, there's a thing in Photoshop called indexed color that'll let you do the same sort of thing now. And so used to, when I would save a graphic as a GIF in Photoshop, it was kind of part of the saving process, and you could kind of mess around with some of that stuff. And by removing some of those colors, then you would get a smaller file size, but it would reduce the quality of the image. But basically, the compression technique for PNG just seems to give you smaller file sizes generally than GIFs do, and so most people prefer those over the GIFs. Is this not working? Huh. Is this plugged out? There we go. It lit up for a second. Okay. Must be that top plug is bad. All right, so that's a GIF. BMPs, which are bitmaps. That's where that name comes from. This is another lossless technique for image encoding, and it uses run length encoding that we learned about. And then finally, the last popular format we're going to list is JPEG, which stands for Joint Photographic Experts Group. So the name itself should tell you that JPEGs were designed with photographs in mind, right? That's what they were, their primary purpose was to come up with a way to compress photographs that still have good quality. So I could take the file size down, but now I can put those photographs on the web. So lossy or transfer all over networks. So lossy compression that breaks an image into 8 by 8 blocks. So it takes the image and separates it up, and then it looks at those 8 blocks and looks at how it can throw information away, right, that you won't notice within that region there, and just kind of rebuilds the image based on that. All right. So I'm just going to really quickly go through compressing video, because video compression, one of the primary ways that you do video compression is, anybody want to take a guess? What is video? Video is simply
A bunch of pictures.
It's a bunch of pictures, right? Video is just a series of pictures of individual images usually presented at 24 or 30 images or frames per second. So if you see FPS, when you're dealing with video, that stands for frames per second. It's talking about how many images that you have when a second goes by in that video, right? And so if video is just a series of individual images, what's an obvious way that we might go about compressing video?
The same way we do
The
images.
same techniques that we use for images. We go image by image, right, through each of those images, and we use some of the same compression techniques that we use on images. So that should be obvious. And what we call that is intraframe, or spatial. Remember intraframe or spatial, I've underlined that one, or spatial compression. Simply runs the same algorithm on each frame. Compressing each individual. So this technique uses the same compression techniques that we just learned about with images. It doesn't really build upon the fact that we're dealing with video. It just says, I'm going to look at each image as its own image and then compress it accordingly. All right, that's called intraframe compression. Now interframe, so we've got intra and inter. Interframe, that's also known as temporal. Compression. Compares frames to each other. reusing redundant pixels from one frame to the next. So this is kind of like what we learned with run length encoding, you know, where it's looking for repeated stuff. It looks at the video file frame by as the frames are related to one another. And so if I go from this image to this next image, and the image is almost identical, but maybe 10% of the image is different in the next image, then it just says I'm going to repeat everything in the previous image, and I'm only going to record new information about that 10% that changed. Right? So if you've got a scene in video where very little motion is taking place or whatever, you know, this compression technique can save you a lot of space, because it's just going to reuse this stuff in this frame from the previous frame. Does that make sense? Yes?
So if you took two identical videos, like same size, resolution, and time, and one of them is just like of that chair, and another one's like someone running in the background, the one person
Right.
would take up more storage.
Yeah, right, exactly. Because we can use this technique for that one of just the chair, because not much changes, right? Exactly. Okay. One other thing to note about digital video is just that, and this is just something to throw out there, right? We have a limited. When you sign up for an internet plan at home, you pick a particular. It's based on megabits per second. Is typically how those internet plans are defined, right? So, like I think the one that we're subscribed to at home is 50 megabits per second. It's supposed to be the max. We never get anywhere near that speed, right? But that's supposedly the max speed that we can ever get. And so, actually, that's not true. I did see a speed over that the other day when I was testing it, which was interesting. So. If your internet connection is 50 megabits, and mega in this case actually means million, because we're talking about the individual bits. So 50 million bits, all right? So 50 megabit internet connection, megabits per second is how that's represented, can handle 50 million bits per second, all right? But then 4K video uses nearly 200 million bits per second. Well, we've got a problem, right? If I want like high quality 4K video in my home, and my video, the pipeline to my house can only handle 50 megabits per second, then there's no way that I'm going to be able to transmit uncompressed 4K video, right? And so that's why these compression techniques that we're talking about are so important, because if you don't compress this data, you're just not going to be able to enjoy it at home. You know, you're going to have a dedicated player hooked up to your TV. You're not going to be able to stream something like that. So compression is critical as we talk about, you know, streaming information over the internet. All right, I really wanted to get into compressing audio, which is my last topic for today, but we're out of time. So here's what I want you to do for next week. I want you to read. You're going to read about the audio next week, and I'll just briefly touch on that at the beginning of the next class. But I want you to read page 76B through 86. I want you to study for quiz 3B. And I want you to download a tool called Handbrake. Is anybody familiar with Handbrake? Download Handbrake. You can find that on, I guess it's a French site, Handbrake.fr. And Handbrake is used for compressing video. All right? So I want you to take a small video. And play with compression. So we did this with images, right? With your tool where you were saving JPEG images. I want you to do the same thing with Handbrake. And what you're going to find with Handbrake is that it's going to, it's got a lot of settings in here that are, that you can mess around with. And honestly, I don't know what all the settings mean, right? But some of the stuff with what we've talked about, some of those things that you see in there will start clicking. And based on the information that we talked about, and just take a simple video, and I want you to play around with compression. Do 3 compressed videos, and like you did with the JPEG, send me an email with discussing the differences. All right, I'll send this out in an email to you guys too, so you'll have it. Yeah, but it's basically the same thing we did with JPEGs, but we're going to do it with video. I want you to play around with that on the video. So, all right, you guys have a good day. See ya.